Hello and welcome back to Module 3 of Statistics. In this video, we're going to tackle the addition rule and the rule of complements. So getting more into some of the more in-depth rules of probability. I'm going to show you how to compute probabilities by using what's known as the general addition rule. We're going to compute probabilities by using the addition rule for mutually exclusive events. We'll talk about what those are. And then we're going to compute probabilities using the rule of complements. These are very important rules, so make sure you're paying attention and taking good notes in this video particularly. Not that you shouldn't have been doing that the whole time, but compute probabilities using the general addition rule. So, A or B events and the general addition rule. So we say an event is a compound event if it's an event that's formed by combining two or more events. One type of way of doing this is the event A or B. This simply means the event A could occur or B could occur or both. And so that would be generally under the rule of A or B. Probabilities of events in that form are computed using the general addition rule. And here it is. For any two events A and B, the probability of A or B is simply the probability of A plus the probability of B, which seems to make sense. But you have to subtract out the probability of A and B. Now, why this subtraction must occur? When you add A and B together, it's possible that A and B could overlap each other, in which case the overlap of A and B is counted in both of these individual probabilities. It's a part of A and it's a part of B. And it doesn't get special treatment. It doesn't want to get counted twice. So we have to subtract out the extra overlap, that extra time of counting them. And so that's why you subtract out the A and B. Okay? So that's the rule there. 1,000 adults were asked whether they favored a law that would provide support for higher education. In addition, each person was classified as likely to vote or not likely to vote based on whether they voted in the last election. What is the probability that a randomly selected adult is likely to vote or favors the law? Keyword here is or. So likely to vote or favors the law. So according to the rule, we would take likely to vote, okay? So we have to add up all the likely to vote. That's the horizontal row, likely to vote. 372, 262, 87. That's 721 people who are likely to vote. So the probability of likely to vote is 721 out of 1,000. Then we would take favors the law, which is this first column, 372 and 151. We would add those together to get 523. So there's 523 people who favor the law. And it makes sense you would try and add those together, right? But the beauty of this, and this doesn't always happen, but in this case, if we just added them together, that would be bigger than 1, and we can't have that, so something's not right. And you will notice the 372 people who both are likely to vote and favored it actually were counted in both of those. They were counted in this sum and in this sum, and we don't want to count them twice. So we have to subtract the overlap. We have to subtract those who are likely to vote and favor the law, which is 372 out of 1,000. So by the general addition rule, we're going to add the 0.721 plus the 0.523 and then subtract 0.372, and that gives us 0.872. So that is the general addition rule. Let's see if you can try one yourself. The following table presents numbers of U.S. workers in thousands, categorized by type of occupation and educational level. What is the probability that a randomly selected worker is a college graduate? So first off, let's just start with that. You would add up all of the college graduates, and then you would divide it by the total. I'm not actually going to run through the totals here because I don't have them, but you would add up all the college graduates and then divide by the entire table total, and you should get 0.342. What is the probability that the occupation of a randomly selected worker is categorized either as sales and office or as production and transportation? So in this case, you would take the probability of sales and office, which would be these two, added together, or production and transportation, which is these two, added together. And then technically you would need to subtract the overlap, but here's the kicker. In this case, there is no overlap. The and is 0 because sales and office is these two, production and transportation is these two. They don't overlap at all. So you actually don't need to subtract anything there. You would just add the individual probabilities. C, and hopefully you get 0.361. C, what is the probability that a randomly selected worker is either a college graduate or has a service occupation? Now, this is where the general addition rule is going to kick in, because you would need the college graduate and you would need the service occupation, which is this column here, or this row here, and they overlap here at the 2385. So you would need to subtract the 2385 from your total, and you get 0.469, hopefully. All right, let us compute probabilities by using the addition rule for mutually exclusive events. So 2 events are said to be mutually exclusive. Sometimes you might see it as the word disjoint, but they mean the same thing. If it is impossible for both events to occur. We just saw an example of this. It was impossible for anyone to be both sales and office and production and transportation. They did not overlap, so they would be mutually exclusive events. Here's some other examples. A die is rolled. Event A is that the die comes up 3, and event B is that the die comes up to be an even number. These 2 events are mutually exclusive, since the die cannot come up both 3 and even, so the probability of both happening is simply 0. A fair coin is tossed twice. Event A is that one of the tosses is heads, and event B is that one of the tosses is tails. These events are not mutually exclusive. If the 2 tosses are heads, tails, or tails, heads, then both events can occur. So we would have to be careful with that. So again, mutually exclusive just means they can't happen together. Suppose that the college student is chosen at random. Determine whether events A and B are mutually exclusive. So event A is the student is older than 21 years, and event B is the student is taking a statistics class. Could those happen together? Well, certainly. You might be in this position yourself. You might be older than 21 years, and you are taking a statistics course. So those events are not necessarily mutually exclusive. The student is an only child, and the student has a brother. I would say those, generally speaking, are mutually exclusive, ignoring things like stepbrothers and things like that. Generally speaking, if you're an only child, you don't have a brother, that's not possible. So that would be mutually exclusive. Now, here's the addition rule for mutually exclusive events. Remember that the general addition rule said that you add A and B together, and then you subtract the probability of A and B. Well, if they're mutually exclusive, the probability of A and B is simply 0. So you're subtracting 0, which doesn't do anything. So it actually simplifies. If A and B are mutually exclusive, it's much easier. The probability of A or B is just probability of A plus the probability of B. But be careful. You want to make sure using this, you want to be so sure that A and B are mutually exclusive. Because if you miss out on subtracting that overlap, that's where you can easily get messed up. So here's an example. In a recent year of the Olympic Games, a total of 11,544 athletes participated. Of these, 554 were from the U.S., 314 were from Canada, and 125 represented Mexico. What is the probability that an Olympic athlete chosen at random represents the U.S. or Canada? Well, they can't be from both. They could be from from the 2 different countries, but they're only representing one country. So being from the U.S. and being from Canada are mutually exclusive here. So the probability simplifies. If I want the probability of U.S. or Canada, I simply add the individual probabilities of U.S. and Canada together. So 554 out of the 11,544 are from the U.S., 314 out of 11,544 are from Canada, so we just add those together and get 868 out of 11,544, which is about 0.075. Okay, so very nice if they're mutually exclusive. In a stats class of 45 students, 11 got a final grade of A, 22 got a final grade of B, and 8 got a final grade of C. Question A, what is the probability that a randomly chosen student got an A or a B? Well, again, it's not possible to get both an A and a B, so these are mutually exclusive. So you would just take 11 plus 22, that's 33 out of 45, which is about 0.733. And then what's the probability that a randomly chosen student got an A, B, or C? Again, these are all mutually exclusive, and this extends past 2 events. It works for 3 events as well, so you can just add them. It'd be 11 plus 22 plus 8, which would be, 41 out of 45, which is 0.911. And then we will now compute probabilities by using the rule of complements. This is a very important rule. let's talk about the complement of an event. 200 students were enrolled in a statistics class. Find the complements of the following events. So we probably need a definition here, and I'm not sure why it's not typed out, but the complement of an event is simply the event not happening. It's just the opposite. So if 50 of them are sophomores, the complement would be that the number of sophomores is not 50. Okay. More than 50 of them are sophomores. The complement would be that 50 or fewer are sophomores. And at least 50 of them are sophomores. The complement would be fewer than 50 are sophomores. It's just the opposite. And because of that, we end up with this nice rule of complements. And by the way, this is the abbreviation. So the probability of A complement, it kind of looks like A to the C, is just 1 minus the probability of A. So if I know the probability of A happening, the probability of its complement happening is simply 1 minus the probability of A. So according to the Wall Street Journal, 40% of cars sold in a recent year were small cars. What's the probability that a randomly chosen car sold in that year is not a small car? Well, being a small car and being not a small car are complements. They're opposites of each other. So since I know the probability of being a small car is 40%, I'd simply take 100% minus 40%, and I get 60%. So the probability of not being a small car is 60%. Again, this is a very important and useful rule because sometimes it's easier to calculate one of these values than it is the other one. So maybe an example I commonly use is if I want the probability of at least one of something doing something, it sometimes might be more difficult to calculate at least one, but it's very easy to calculate the complement, which is that none of them are. And so the complement rule is very useful in those situations. So you should know how to use the general addition rule to compute probabilities of events in the form A or B. You should know how to determine whether events are mutually exclusive or not, whether they can occur together or not at all, how to compute probabilities of mutually exclusive events, how to determine the complement of an event, and how to use the rule of complements to compute probabilities. If you have any questions about any of these rules, please let me know.